All right, so welcome to Recitation 9 on Mechanics and Materials 1. Also today we have 4 questions to go through together. This is the first one. All the questions deal with the topic torsion. So we are done with axial loading, and now today is the first recitation on torsion. So there is a steel tube having an outer diameter of 60 millimeters. So 60 here is the outer diameter, used to transmit 6.75 kilowatt when turning at 27 revolution per minute. Determine the inner diameter D. So this D is the inner diameter of the tube. The inner diameter of the tube to the nearest millimeter if the allowable shear stress is 70 megapascal. Now, what we want to do is basically to make sure that the shear stress that is developed in this tube is less than 70 megapascal. All right? Now, if you remember, for a torsion problem of a shaft, tau is related to torque T via the formula TR over J. Now, the maximum shear, therefore, would occur as R will be the maximum R, right? So maximum R here in this problem is the outer radius, which is half of 60 millimeters. So that is 30 millimeters, or 0.03. So we have that. J is pi over 2. This is the polar moment of inertia. The formula was pi over 2 CO to the power 4 minus CI to the power 4. Now, this is inner radius, and CO is the outer radius. Okay, so for the shear stress, we know the maximum allowable limit here would be 70 megapascal. So we insert 70 megapascal, sorry. It would be 70 megapascal, so we also insert that here. Okay, so basically the formula we have is 70 megapascal, 10 to the power 6, equals T R max, which is 0.03 divided by pi over 2. Now, external radius, which is that 0.03 to the power 4 minus that CI, or internal radius, to the power 4, which is the unknown of the problem. So the problem asks you to calculate CI, basically. This is your unknown. The only thing remaining here is that we don't know yet what T is. But if you remember, for T, for the torque developed in shafts when transmitting power, we had a relationship between power and torque. So P would be T omega. P is given, that is 6.75 kilowatt. Let's say the rotational velocity, omega, is also given, that is 27 rev per minute. And from this, we should be able to compute T. The only thing that you need to be careful about is that this omega is expressed in terms of revolution per minute, so you need to transform it to radian per second to have, let's say, consistent units. So in order to do that, you would basically say omega 27 revolution per minute. And then you would maybe say 1 minute is 60 seconds. And you would say, I don't know, 2 pi radian is 1 revolution. So by doing that, you would basically cancel these together, and you would end up with your omega in terms of radian per second, and that would be 0.9 pi radian per second. Okay, so you insert that in your formula here, and from that you get T, torque. So torque is then basically 6.75 10 to power 3, because it was kilopascal, sorry, it was kilowatt divided by omega, which is 0.9 pi, and that gives you 2.387 to the power 3. 10 to power 3 Newton meter. So this is your T, and all you have to do now is to insert this value in this equation. Okay? So if you do that, then you get one equation in terms of CI, and you can just, let's say, solve it in terms of CI. Okay, so that's exactly what you do. You just insert that here, and from that you get CI to be 0.01996, okay, which is basically 19.9 millimeters. And then if you wanted to calculate that D is the diameter, so it's 2 times CI, and that would be, let's say, 39.9, almost 39.9 millimeters. Okay. Now, the question asks you to express this in terms of the closest millimeter. So this is something that you need to be careful, or the nearest millimeter. This is basically the idea is that if you want to buy these, I mean, if you want to kind of make it yourself, maybe you can just make it at any diameter you want. But if you want to buy this, or if you have limitations in your devices, then you need to have perfect sizes that are basically available to you in handbooks or in this, in stores. So for that reason, it asks you to sort of change it from being, having a digit here to something that is in full millimeters. Okay. So in your usual approximations, you would just say, well, this is the closest number to 40 millimeters. And this would be fine. Okay, so you can just say that's the answer. But from your engineering, let's say, intuition perspective, you should also be careful about this. So if you round this up, so if you say it's 40 millimeters, that means you are rounding it up. But this is the inner radius. So if you make the inner radius larger, you basically make that shaft thinner. The thickness would be less. So you make it more vulnerable. Or eventually your T is, your stress would exceed your maximum stress, okay? So the correct way of doing it would be to basically choose 39 millimeters, not 40 millimeters. Although, again, mathematically, this thing is shouting at you that you should do 40 millimeters because it's so close to 40. But if you do 40, you make it worse. So from engineering perspective, we would take 39. Does that make sense? Okay. All right, so that's the first question. Okay, so here is the first question, is the second question. We have a steel shaft made from a particular A36 steel, which has it's a solid shaft, so it's not a hollow shaft like the previous example. It has the diameter of 50 millimeters. So the diameter here is 50 millimeters. And is subjected to distributed and concentrated loading as shown in the figure. Determine the absolute maximum shear stress in the shaft and plot a graph of angle of twist of the shaft versus x. Okay, so this is your x coordinate. We want to know what is the angle of twist, but also we want to calculate the maximum shear stress. Now, pay attention to the loading here. There is a loading here. So this is, let's say, counterclockwise, 250 Newton meter. This is a concentrated moment. And then you have all these little distributed moments, which is 200 Newton meter per meter in the first half of that shaft. Okay, so this is the loading condition you have. Now, for this particular problem also, just to have it, when you know the material is made from this particular steel, it basically tells you that you can use a particular material property from handbooks. And for this one, we know that G, shear modulus, is 75 gigapascal, okay, or 75 10 to the power 9 Pascal. Okay, so we have two problems or two questions to answer. The first one is the maximum shear stress. So in order to answer that, we remind ourselves of the formula for stress. So if you have tau as the shear stress, tau is TR over J. Now, that tells you if you are looking for maximum tau, then you would have it at maximum R. So it happens at the outer part, or the, let's say, the outer boundary of the shaft. And then we said this R max, we just call it maybe C in this case. And we know the diameter is 50 millimeters, so that C is just 25 millimeters. Okay, so we have that. We know tau max is TC over J. Now, we have a shaft. All over the shaft, the outer radius is constant, is 25 millimeters. J is constant because the cross-sectional area is not changing. But T is not constant, okay? So T here is different from, well, from here, from here, from here, okay? And this T is your internal torque. We need to calculate that, all right? Obviously, the maximum of tau max would occur where T is also maximum, okay? So the question now is, what is T maximum? So we need to calculate the torque distribution itself. And then again, pay attention to this very important point. These things that you see here, so these 250 and 200, these are external torques, okay? These are external loading. This is not what enters into this formula. When you are using formula like this, you're actually calculating what is happening inside the shaft. So you need to find internal loadings, okay? So don't use the external ones here. All right, in order to do that, I always encourage you to draw a diagram like this and just plot the distribution of the moment. Okay, so let's say this is point B, this is point C, and this is point A. Let's just draw the distribution of torque T throughout this member, okay? Now, if we cut it somewhere here, we would have a slightly complex loading, because if you think about, let's say if you look at it from the right-hand side, you have a little distributed load plus this concentrated load, okay? And if you look at it from the left-hand side, the same thing. There would be distributed load and then a concentrated load from the support. Okay, either way you can do that, but I find it easier to cut it from the left-hand side. So we will do that. To start, let's calculate the reaction at the support A. So you have 250 Newton meter counterclockwise, right? And then you have this 200 Newton meter per meter clockwise distribution for 0.5 meters. So now, if you multiply that by 0.5, you get 100. So that means you are applying 250 counterclockwise, and then you compensate for 100 of it. So in order to have equilibrium, the support A need to compensate for that remaining 150, okay? So you get 150 also at the support A. Does that make sense? So now you have equilibrium basically. By the way, I told you when you have a problem like this, and if you find these arrows misleading and you don't like torsion problem, you can always think of them as our usual extension problem. Just think about it as distributed loading, okay? This 250 counterclockwise, it would be an arrow which is 250. Now, you have these little distributed arrows of 200 for 0.5, okay? That effectively, all of them will give you 100. So you would need 150 from the support to keep this thing in equilibrium, okay? The only thing is that here, instead of one arrow, you need to draw double arrows because they are, they are torques, not forces. Okay, so if you look at it like this, I think it makes more sense to you, maybe. Okay, anyway, at A, we know it's 150. Now, if you cut it somewhere here, you would have 150 plus that slope of the line, which is 200 times x. You get that much moment. So you start at 150 at A, and then you would have this line, and the slope of the line is 200. So the line equation itself is 150 plus 200x. Okay, so this is t as a function of x if x is between 0 and 0.5. All right, so from A to C, that's what happens, and then at C, you would have exactly 250, therefore. Now, at that point, you apply your 250 concentrated moment, and then you get 0 between C and B, obviously. There is no moment between C and B. So this is your distribution of your internal torque. Okay? Pay attention that I'm using this with plus sign. So if you look at these, they are clockwise. Okay, so maybe you would be tempted to think these should be minus. But be careful. When I draw this, I am talking about the moment or a torque that you would have inside. Okay, so this is the internal one. It would be the same as if you cut this thing here. If I cut this thing here, what I need inside to cancel, the contributions from this would be towards right, and that's what we counted as, plus convention. Okay, so the internal torque is counterclockwise in this direction. So we are using again our let's say convention that if you think of it this way, then counterclockwise on this side is plus. All right. Okay, I said counterclockwise, but I think I drew clockwise. So this would be more like this. Okay. All right, I think this is the most, it's very easy, but this is the most complicated part of this question. If you don't get confused in this part, if you properly draw this graph, the rest is very simple. The rest is just using the formulas. Okay, so now remember we wanted to calculate the maximum shear stress. And in order to do that, we were looking for maximum T. Now you can clearly see what maximum T is. Maximum T is 250. Okay, so now all you have to do is to use that formula with these numbers. So tau max is that 250 times maximum radius, or C, which is 0.025, divided by J. J is pi over 2. It's a solid shaft, 0.025 to the power 4, and that gives you 10.2 megapascal. All right? Before I jump to the next part, I want to also mention this to you, that the fact that I cut it from the left-hand side is just a matter of convenience. You could have done the same thing here. So you could have cut it from the right-hand side. Now, if you did that, this distance is 0.5 minus x. Okay, it's not x, which you can then multiply it by 200. 200 is the density again. And then subtract that from 250. If you do that, you also get exactly the same equation of 150 plus 200x for the distribution of t. Okay? So it doesn't matter how you cut it. If you cut it carefully and if you write the equation carefully, you get to the same equation for that line. All right. So this was the first part of the problem. We know what is the absolute maximum shear stress. Now, for the second part, the equation asks us to calculate the angle of twist. And you remember the angle of twist, basically for a distributed load, or in its generic form, would be an integral from, let's say, 0 to x of tx dx divided by gj. All right? Now, in general, g and j could be a function of x, but in this case, they are constant. G is simply 75 gigapascal, or otherwise 75 times 10 to the power 9. J is exactly what we had up there, pi over 2, 0.025 to the power 4. And t has two parts, okay? So for this integral, we need to think of two sides. If x is between 0 and 0.5, and x is between 0.5 and 1. So here, t is simply 0. We can see it up here. So between C and B, t is 0, so there is no change of angle. All right? Between A and C, so in the first part, the equation, though, is what we just had. So t would be a function of x, and that is 150 plus 200 plus 200x. All right? So that's all you need to do. For the second part, the integral would be 0, so it disappears. For the first part, it's going to take this shape. So you just say this would be basically an integral from 0 to x, and x is between, or x is less than 0.5, then 150 plus 200x dx divided by gj, as I mentioned. And, you just need to integrate this. This is very simple. You can imagine this gives you something like 150x plus 100x squared, right? And then if you put 0, you just get 0. If you put x, you just get x. So basically, you get exactly the same thing, and then you divide by gj. And if you do that, you will get an equation for your phi, which would be obviously quadratic, as I just mentioned, and it would look like 3.26 times x plus 2.17 x squared times 10 to the 10 to power minus 3 radian. All right? So this is for any x that is between 0 and 0.5. And for any x larger than that, phi is just constant. So what we want to do now is to draw that. So the question asks you specifically to draw a graph of this. Now, if I do that again, this is, let's say, point A, that's point C, and eventually that's point B. At point A, we have the support, so we know angle of twist is 0, it's fixed. And then you have this quadratic equation which keeps increasing up to point C. So you would get something like this. And then between C and B, you would just have a straight line because T is 0, so there is no change of angle of twist. So this would be phi. And as I mentioned, this quadratic equation is basically this one. And if you want to know where you get the maximum or the angle of twist at C, this would be that, which is 0.00217 radian. All right? So that's it. Now, just before we jump to the next example, maybe you have a good feeling that, when your internal torque is linear here and is 0 here, maybe you expect to have a quadratic line for angle and a constant here, So it kind of tells you that your T is something like your phi prime, okay? So if your phi was constant here, its derivative is 0, and then if your phi is quadratic, its derivative is linear, okay? Which basically you can see from this integral, okay? So let's say that intuition is not so physically wrong. All right? Okay, so we come to the next example then. We have a turbine that develops, so this is, let's say, the turbine at point B. It develops 150 kilowatts power that is transmitted to the gears such that both gears at C and D, they carry equal amount. Okay, so let's say they take 75 each. So this one has, you want to say it has the power of 150 kilowatts. Then at C, you get 75 of it. And at D, you get 75 of it. Now, this is an assumption of the question, okay? If the rotation of the 100 millimeter diameter A36 steel shaft is 500 revolution per minute, determine the absolute maximum shear stress in the shaft and the rotation of B relative to E. And this bearing at E, it doesn't do anything. It just allows for, let's say, simple rotation without applying additional torque. Okay, so how do we do that? We do exactly what we did previously. The first thing we want to do is to calculate the absolute shear stress. So we remember, again, shear stress is related to torque via tau equals T R over J. And then again, if we want the maximum of that, this R should be R max, for which we use the letter C. And that would be half of the diameter, so that is 50 millimeters, or 0.05. It's a solid shaft, so J is simply pi over 2, 0.05 to the power 4. So we have this and that. Now, if you want the maximum tau, you get it where T is maximum, okay? So now if you look at this picture, T would be maximum between B and C, right? So between B and C, that torque will carry all the power. Between C and D, it carries only 75 kilowatt of that power. And between D and E, it doesn't carry anything, so it's 0. So you can draw that T diagram again for your reference. So let's say if we want to draw the internal T, and then I say these are the points B, C, D, and E, and then let's say this is T, we would have all of it here between B and C, and then we would have half of it between C and D, and then eventually nothing between D and E. Okay, so this is how that internal torque is distributed. Now, what are those numbers? I mean, I just drew it, but what is this T actually itself? In order to answer that, we need to use our formula again. P equals T omega. So we know the power. So between B and C, for instance, the power is 150 kilowatt. Then we can calculate T for that given omega, or rotational velocity, if that is 500 rev per minute. And then again, we do our trick to change that dimensions or units. So 1 minute per 60 seconds, and then let's say 2 pi radian per 1 rev. We do this so that we can cancel these and get something in terms of radian per second. And also on the right-hand side for kilowatt, obviously you do 10 to the power of 3 watts. So you just insert this and you get T between B and C to be, so that's the full torque, 2,864.8, let's say. Okay, so that's 2,864.8, and then half of it would be transmitted to C. So in CD, then you have half of what is left, which is 1,432.4 Newton meter. Okay. So if you wanted the maximum shear stress, obviously that maximum shear stress occurs between B and C, because T is larger, and now in your formula you can use that. So tau max is again TC over J. For this T, you would put your TBC because it's the largest, it's the maximum T. For C, you put the outer radius, so 0.05, and J, I just mentioned, it's pi over 2, 0.05 to the power 4. So you do this and you get your tau max as 14.6 megapascal. All right, so this is the first part of the question. It asks you to calculate the maximum shear stress. In the second part, it asks you to compute the rotation of end B with respect to E. Okay, so basically the angle of twist in the shaft. Now, for this, we remind ourselves of the formula we had for the angle of twist. So remember, phi with respect to phi of, let's say, B with respect to E would be phi of B with respect to C plus phi of C with respect to D plus phi of D with respect to E. So again, remember, so B with respect to C, C with respect to D, D with respect to E. That would be B with respect to E. So that's exactly what I'm writing here. Now, for each of these, you can use our formula. Remember the magic formula for angle of twist is phi equals TL over GJ, which again, if you remember, this would be the equivalent of the formula we had for axial loading, which was delta equals PL over EA. So we use that formula, so it would be TBC times LBC divided by GBC, JBC. Now, G and J are constant throughout the shaft, but I keep them writing as if they will change for completeness. So then it would be TCD LCD divided by GCD JCD plus TDE LDE divided by GDE and JD. Okay, so what are these numbers? Between D and E, T is 0. Between C and D, we have it up here in the graph. And between B and C, we also have it. So we just insert those numbers. So that's 2,864.8. That's 1,432.4. The length of BC is 3 meters. For CD, that's 4 meters. So there's a little difference. And G and J, we just have it up there. So this is, again, 75 gigapascal, also 75 gigapascal. And for J's, we just, we have the J's here. It's the same J everywhere. Okay, so if you do that, you just calculate your angle of twist from B, or B with respect to E, and that would be 0.0195 radian, or otherwise 1.11 degrees. Okay, so this is your angle of twist. All right, that was it for this question. Do you have any question? Okay, if not, then we jump to the next and last example. So you have a hollow steel shaft with a length of 2 meters and the outer diameter of 40 millimeters. When it is rotating at 80 radian per second and it transmits 32 kilowatt of power from E to G, we want to determine the smallest thickness of the shaft such that we do not exceed the allowable shear stress of 140 megapascal. But also we have a second requirement. So this is the first requirement. The first requirement is that we should not exceed the allowable shear stress. The second requirement is that the shaft is restricted not to twist more than 0.05 radian. Okay, so we want to solve this problem. So the question is, what is the smallest thickness? This is the question. We want to calculate the smallest thickness such that it satisfies these two conditions. So we solve it for the first condition, and then we see how the second condition would influence that. Okay, the idea is very, very similar to what we had previously. So again, for this, we use our formula P equals T omega. Again, P of the motor is given. That is 32 kilowatt equals T times omega, that is 80 radian per second. So this gives us T of 400 Newton meter. Okay? So that's that. Now, we calculate tau as our formula TC over J. Now, remember, this is a hollow shaft. So we would have TC over J, that is pi over 2 outer radius to the power 4 minus inner radius to the power 4. Okay? Now, the outer radius is given, so it's 40 millimeters diameter. So your outer radius CO is 20 millimeters, or 0.02 meters. And then the same holds here. So this C, or the outer radius, it would be also 0.02. T is 400, as we just calculated. We are having a limit for tau that's 140 megapascal. So we want this thing to be less than 140 megapascal. Okay? So if you calculate this, so if you just set it equal, so if you say TC over J equals 140 megapascal, this gives you that inner radius, CI, to be 0.01875 meters. Okay? Or let's say 18.75 millimeters. Does that make sense? So you got that. Now, if I make that radius smaller, would I make this worse or would I make it better? This is the question we want to answer. Okay? So remember, for the second part, we are going to calculate that inner radius such that the angle of twist is less than, what was it? 0.05 radian. Now the question is, if I have a radius here, so from the second part, if I end up with a radius that is less than this, would it make this better or worse? Does that make sense, the question? So let's look at the formula. Here, CI, it comes with a minus. So that means if you decrease that, this number would get larger, right? If this number gets larger, it means the denominator is getting larger, right? So the stress that it corresponds to, it becomes smaller. So it is a good thing to reduce it. It's fine if you reduce it. So what I'm trying to say is that we just said CI is 18.75 millimeters, but you could have just said it's less than equal. So anything less than that is on the right side. It's on the good side, okay? Which makes sense. If you make it smaller, you basically make it thicker, right? So remember, this is a hollow shaft, and the outer radius is constant, right? So making this CI smaller, you kind of expect it to help us because you basically make it thicker, right? Okay, so this is the first part. Now, we are going to solve the second part. We set the angle of twist 0.05 radian, and if we end up with a radius that is smaller than this, then we are fine. That's basically the idea. Okay, so for the second part, it's very simple. Phi is now TL over GJ. Uh, Length is 2 meters, T is 400. We got G 75 gigapascal again, and we have J as our formula pi over 2, 0.02 to the power 4 minus our, well, Ci to the power 4. And if we do this, then we get Ci to be 0.01247 meter, or rather 12.47 millimeters. Okay. Just to be clear, let me just remove this to have the, okay, and I do the same thing here. So now we get a Ci that is at 12.47 millimeters. You can play now the same argument here. So if I decrease Ci, if I have any number that is less than this, it would decrease J. Sorry, if I decrease C, it would increase J, which would decrease phi, that is on the safe side. So any Ci less than this is also useful. Does that make sense? So now, the question asks you for the smallest thickness. That means you want to take this. Okay? So from these two, we pick the Ci, and that gives us thickness, which is CO minus Ci, to be 753 millimeters. All right? Now, again, remember, any number larger than this is also fine, but you want the smallest one, okay? So that's the idea of the question. So that's the smallest thickness you can have. All right, do you have any question? Okay, if not, that was the last exercise.